In this example, we're going to look at how intersection and collision questions can be extended to 3D with the important notation that simply graphing paths is not going to be as helpful. If we imagine drawing some path in 3D with 3 axes here versus some other trajectory, we can see very quickly that our human eyeballs are not good at determining whether this is a crossing, a near miss, or anything else. We really do need to go down to the algebra, down to the numbers, or down to the symbols to be able to recognize whether we have an intersection, a collision, or nothing at all. So let's look at that through the lens of an example. We have 2 trajectories again here, r of t and u of t, and we're asking whether the trajectories cross. So cross is the same as intersection. And that, we saw earlier, was the same point and possibly different times. So we have to allow for that. So we're going to take the same approach we used earlier, and we're going to imagine that we're tracing out the r path, and that r path, making it look like a vector over top here, we're going to use t for that, and we're going to use a different time value for u. We're going to use a different variable. We're going to call it s. And we're interested in having the same x, y, and now z value at r of t and some other point u at some other time value s. So we're going to set up our equations there and see what we can find. To start, we're going to look at the x-coordinates, and again, r of t on the left-hand side each time and u of s on the right-hand side. The x-coordinate, we'll have to have t equals, let's gather these, 1 plus 2, not t's, but s's. And then repeat. We're going to have the y-coordinates equal to each other, t for the r-coordinates, 1 plus 6, not t, but s's, for the u path. And last but not least, we're going to have our z's, and they are going to involve t cubed and 1 plus 14 somethings, but it's not t's, it's going to be s's again as well. And there we are. These are the conditions which, if we can find a solution, represent an intersection between the 2 paths. Let's see how we can work through this. It looks like equation 1 is going to be the easiest to work with, simply because it's all linear again. So if we look at equation 1, and it's not super critical. Actually, we have t equals t squared here. We might as well make our lives a little bit easier and simply sub this t into this value and see what happens. We could also solve for s and do that into equation 2 as well. There's really no right way to do this. There's pros and cons for how the equations are going to look either way. We'll try this easy one though. We're going to sub t into here, so we're going to have t squared, but t squared is the same as 1 plus 2s. It has to be to satisfy equation 1, and then the other side of this is 1 plus 6s. If we do that, then we want to be able to solve this. It's just a quadratic, but we have to expand it out a bit. So we're going to have 1 plus 4s, we've got a perfect square here, 4s squared, 1 plus 6s. And if we bring everything over to this side, we'll have 4s squared. We have a plus 1 and plus 1. Oh, that's going to cancel. And we're going to have 4s minus 6s. That'll be minus 2s by the time we're done. And that is nice because there's an s factor. 4s minus 2. And we can even take that one step further if we want. We can divide by 2. And we'll have s and 2s minus 1. And that gives us either s equals 0 or 2s minus 1 equals 0, which is equivalent to 2s equals 1, which is the same as s equals 1/2. All right, so to satisfy 1 and 2, so let's put that in here. To satisfy 1 and 2 here, we have to have one of these 2s values. And we can even get a little more precise, because to satisfy 1, we have to satisfy equation 1 specifically. So t would have to be equal 1 plus 2 times s. Let's put the 1 in here, and the 1 in here. 1 plus 2 times s, but s is 0. So t would have to equal 1. And here t would have to equal 1 plus 2s, 1 plus 2 times a half. That would be 2. So summarizing, we have s equals 0, t equals 1, or s equals a half, t equals 2. Those are our two possibilities that satisfy the x and y coordinates. What we need to do next is still check that the x, or the z's rather, intersect. So I still need to check the z's are equal. We don't have to look at any other values because these are the only pairs that are going to satisfy 1 and 2. We're actually going to grab this and copy it over to the next page, and then we're going to look at our cases. So check 3 with s equals 0, t equals 1. The left-hand side is t cubed. That's 1 cubed, that's 1. And the right-hand side, therefore, is going to be similar. It's going to be 1 plus 14 times s, but s is 0. No, that's 1 as well. Excellent. S equals 0, t equals 1, gives the same z value. Check. And then we check 3 with the other value, other pair of values, the other time options, with s equals a half and t equals 2. Left-hand side of this equation is t cubed, but t cubed is the same as 2 cubed for this point, and that's 8, while the right-hand side is 1 plus 14s, but s is a half for this test point. 14 times a half. That's much better known as 7 plus 1 is 8. These are equal. Should have emphasized that up here as well. So s equals a half, t equals 2 also gives the same z. So what we found are two sets of time values which produce the same x, y, and z coordinates. And the question was, well, where do these actual intersections occur? For, let's just don't do a double check here. It's always reassuring to see our numbers work out all the way through it. So for s equals 0, t equals 1, we have r of 1 is equal to, so the t, remember, went into the r function, and it tells us that at time 1 for that trajectory, we're going to be at 1, 1 squared, 1 cubed. Well, that's conveniently 1, 1, 1. And u at s equals 0, so a little bit earlier, we think u passed through that same coordinate, and 1 plus 2t, but s is 0, so it's 1 plus 0, 1. 1 plus, oh, hey, you see the pattern coming up here? 1, 1, 1. So both of those trajectories go through the same point at different times. Just to compare and contrast, for s equals 1/2 and t equals 1, again, try not to get these mixed up. It's awkward with the labeling list that I did there. But r, which we use the time value t, when it's evaluated at 2, my apologies. The second solution was 1/2 and 2. R of 2 is going to be 2, 2 squared, 2 cubed, or 2, 4, and 8. And u of 1/2 is going to be 1 plus 2 halves. That's 1 plus 1. Hey, that's 2. Excellent. 1 plus 3, sorry, 1 plus 3, because 1 is 6 halves. Not surprisingly, because we solved these earlier, we get the same coordinates for all three. So we get our intersections at 2, 4, 8 and 1, 1, 1. Just summarize that here so we don't have to use a new page. Intersections at 1, 1, and 1, and 2, 4, and 8. Exactly 2 intersections between these two trajectories here, which is a nice segue into what about collisions? Do these particles collide? If they do, at what time and at what xy location would the collisions occur? Well, the nice thing about doing this in this process in this order, where we allowed different time parameters for the two trajectories, s and t, is that if there was a collision, we would have gotten a solution just with the same s and t values. We saw that earlier in another example. So there are no solutions for the same x, y, z at the same time. We would have found them earlier with s equal to t as a condition. And that tells us right away that there's only the two intersections that we found earlier. And specifically answering this question, there are no collisions at all. And that's it. So again, knowing how to set these up, knowing how to set the conditions for collisions versus intersections is what we're looking for you to retain out of this, the logic behind it, and also, where possible, if you have the graphical understanding as well, where you can imagine the trajectories going through space and time, what does it mean to have those paths, those trajectories intersect versus having the particles collide in a visual sense as well.